So rational functions in A-level Math P1 is very brief. There is not a lot in it. There are just two cases. Now rational functions, the main problem that is a part of functions, the main problem that comes in this chapter is in finding the domain or the range of the rational function, and that is because in rational functions there is a new concept of asymptotes. So what are asymptotes? Asymptotes are lines which meet the curve at infinity. For example, in the tan graph, we've done the tan graph. So the tan graph is in tan x at 90 degrees. The graph goes like this, right? So this dotted line is the asymptote to this graph because it will meet this graph at infinity, and we show it like this, that it's approaching the line but not touching it. And then this is 180, so it's somewhat like this. So this is the asymptote, right? That is the concept of the asymptote. Now there are two cases of rational functions in A-level Math P1. So the first case is when you have a constant upon a polynomial of degree 1, or you have a polynomial of degree 1 upon a polynomial of degree 1. There can be two types of asymptotes, the vertical asymptote and the horizontal asymptote. Asymptotes are vertical and horizontal. So a vertical asymptote is the value of, basically it's the equation of a line that is vertical, right? So it's going to be x equals something because it's going to be vertical, right? So it's basically a line at which the curve is undefined because we don't know that what is the value of the curve at this line. It's infinite, right? It's undefined. So that means that if this curve has to be undefined, so if its denominator is 0, so anything divided by 0 is undefined, right? So if the denominator is 0, that means that this curve will be undefined. So to find the vertical asymptote, we equate the denominator to 0. Equate denominator to 0. So for in this case, or in both cases, it is the same. So cx plus d equals 0. So vertical asymptote will be x equals negative d upon c. Now the horizontal asymptote is different in both cases. So horizontal asymptote, the vertical asymptote was the value of x at which the curve was undefined. Now the horizontal asymptote is the value, so the horizontal asymptote is the value of y when x is undefined or infinite, right? For example, in the basic graph of 1 over x, the graph is something like this, right? So when x is very large, so what will be the value of y? That is represented by the horizontal asymptote. The horizontal asymptote over here is the x-axis. So this means that when x is very large, so y will be 0 because it is the x-axis, so y is 0, right? So the horizontal asymptote is the value of y when x is very large or undefined, right? So to find the horizontal asymptote, what we'll do is we'll take the highest power term common from both the numerator and denominator, right? So I'm taking x common from both the numerator and denominator. So x common from the numerator gives b upon x, and from the denominator gives c plus d upon x. Now again, horizontal asymptote was the value of y when x is very large or undefined. So from this we get that if anything is divided by infinity, it's 0, right? So when x is very large, it's undefined, so b upon x will become 0, right? So if the numerator becomes 0, so the horizontal asymptote will be 0, that is y equals 0. For the second case, again taking the highest power term common, that is x, So x a plus b upon x c plus d upon x. Now when x is very large, it's undefined, so b upon x is 0, d upon x is 0, right? So this is x times a, that is 0, upon x times c. So x and x get cancelled. So the horizontal asymptote is a upon c. So for the vertical asymptote, the method is that we equate the denominator to 0. For the horizontal asymptote, now the shortcut that we can use is that in our syllabus there's only maximum power of x as 1 in maths. So you can use the shortcut that if we have an improper rational function, that is the numerator has x power 0 and denominator has x power 1, then always y equals 0 will be the horizontal asymptote in this case. And if we have x power 1 as the maximum power in the numerator and also in the denominator, then the horizontal asymptote will be the ratio of the coefficients of x, that is a upon c. It will always be the ratio of coefficients of x. So this, now once we found the asymptotes, we can use those to sketch the graph. But once again, this is not mandatory in our syllabus. You can find the range and domain without this, but this will help you find the range more easily. So the first graph is y equals 3x plus 2. Now I'll find the vertical asymptote by equating the denominator to 0. So x minus 2 equals 0. Therefore x plus 2 equals 0, x equals minus 2. And the vertical asymptote, because we have the numerator with maximum power x power 0, so the horizontal asymptote will be directly y equals 0. So I'm doing this roughly. The horizontal asymptote is the x-axis, right, because it's y equals 0. The vertical asymptote is x equals negative 2, so it's over here. Now we've drawn the asymptotes. One thing that we have to check right now is that are there any x-intercepts or y-intercepts. So if we put x as 0, right, we'll get y as 3 upon 2, that is 1.5. So this is the y-intercept, and if we have y as 0, then we won't get any value of x, so that means that there is no x-intercept, right? So we can now sketch the graph easily. This is one asymptote, this is the second asymptote, so the graph will be like this. It will be approaching the asymptotes but not touching them, right? One will be over here. Now this we determined because there was the y-intercept over here. Now how to determine where the next part of the curve will lie? So we can take any value before the asymptote. Let's take negative 3. So negative 3 plus 2 will give us negative 1. So 3 upon negative 1, right? 3 upon negative 3 plus 2, this is negative 3. That means that the second part lies below the x-axis and obviously left of the asymptote. So it will be somewhat like this. We're just sketching it, so it doesn't matter if it's precise, accurate. Now the second graph is 2x plus 3 upon x minus 1. The vertical asymptote will be x minus 1 equals 0, that is x equals 1. And the horizontal asymptote, now over here the degree of x is same in numerator and denominator, so we can take the ratio of the highest power terms, that is 2 upon 1. So y equals 2 is the horizontal asymptote. Vertical asymptote is x equals 1. Horizontal asymptote is y equals 2. Now we'll find the intercepts. So is there any x-intercept? For an x-intercept, y should be 0. When y is 0, we'll get 2x plus 3 equals 0. So x equals negative 1.5. So this is the x-intercept. For the y-intercept, x is 0. So if we have x0 over here, x0 over here, we'll get y equals negative 3. So over here. So one part of the graph, it has to be parallel to the asymptotes approaching them. So one part of the graph will be like this, right? And the second part will lie over here, and we can check that using the equation. If you put any value of x that is towards the right of the vertical asymptote, let's take 3. So 2 times 3 is 6, 6 plus 3 is 9, and then 3 minus 1 is 2. So y equals 4.5. That means that it's above the horizontal asymptote, so it will lie in this region. So in this question, we've been given a rational function 5 upon y minus 3x, and they're asking for f inverse x. So I'll write y equals 5 upon 1 minus 3x. Y equals, 1 minus 5 upon y equals 3x. This becomes y minus 5 upon y equals 3x. So x upon y minus 5 upon 3y. So f inverse x is x minus 5 upon 3x, right? Now we have to find its domain and range, right? So what I'll do is I'll sketch this curve. Its domain will become the range of the inverse, and its range will become the domain, right? This can be done without sketching the graph, but it will be easier to do it with the graph. So first, finding the vertical asymptote of fx. So vertical asymptote is denominator equals 0. So 1 minus 3x equals 0. So x is equals to 1 upon 3. For the horizontal asymptote, because the numerator has no x, so that means that the x-axis will be the horizontal asymptote. So this is the horizontal asymptote, that is the x-axis. Vertical asymptote is 1 over 3. So let's say this is 1. So 1 over 3 is somewhere here. Right? But what they've said is that x is greater than or equals to 1. So I'll find fx at 1. So if x was 1, so we'll get 5 over 1 minus 3, that is 5 over minus 2, so minus 2.5, right? So that means that at 1, y is minus 2.5. This is minus 1, minus 2, minus 3. So the graph starts here and it's greater than that. So if you sketch the graph, it will go somewhat like this. And how do we know that? Because this is the horizontal asymptote, so it can't touch that. And because it's starting in the negative region, so it has to stay in the negative region, so it will move like this, right? So to find the range of this, the range will be fx is greater than or equals to this value, that was negative 2.5, but it's less than or equal to 0, right? Because it can't go above the x-axis. So now the range of f inverse will be the same as the domain of f, that is greater than or equals to 1, but the domain of f inverse will be the range of f, that is this. Sorry, one mistake, it won't be less than equals to, it will only be less than, because it can't touch the graph, right? It's always below, it can't touch the x-axis, it's always below the x-axis. Next question, they've given us fx and gx, right, as two rational functions, and they're saying find and simplify an expression for fgx and state its range. So what will be fgx means we're inputting g into f, so 4 upon g, that is 4 upon 5x plus 2 minus 2, right? So 4 divided by this, it will be 5x plus 2 minus 2, that is equal to 5x. So fgx is equal to 5x. We have to state its range. So over here, basically this is a composite function, which means that the domain of g will become the domain of fg. Domain of g was x is greater than or equal to 0. That is the domain of fg. So if we input x as 0 in 5x, so we'll get 0, and it can be greater than that. So that means that the range of fgx will be greater than or equals to 5. Sorry, I meant greater than or equals to 0 because x is 0, so fg is also 0, so greater than or equals to 0, right? Now the second part, find g inverse x and find its domain. So firstly, gx is 4 upon 5x plus 2. So for g inverse, I'll take gx as y. 5x plus 2 equals 4 upon y. So g inverse x is equals to 4 minus 2x upon 5x. Now they're saying find its domain, right? So its domain will be the range of gx. So I'll plot gx, I'll sketch gx, and I'll find its range, which will be the domain of g inverse. So again, first we'll find the vertical and horizontal asymptotes. So vertical asymptote of gx will be 5x plus 2 equals 0. So x equals negative 2 upon 5, that is negative 0.4. Horizontal asymptote will be y equals 0 because it's an improper rational function. So y equals 0. So negative 0.4 is the vertical asymptote, right? Negative 0.4. But then they've given that x is greater than or equals to 0, right? So I'll find the value of gx at 0, matlab g0, that will be 4 upon 2, that is 2, right? So when x is 0, gx is 2. At x is 0, gx is 2. So this means that if we plot the graph, it has to start over here, right? It can't be before that because x is greater than or equals to 0. So it will go somewhat like this because it has to approach the horizontal asymptote, but it cannot touch the horizontal asymptote, right? So it's basically the range for this, range of gx will be, it's greater than, not equals to, it's greater than 0, and it's less than or equals to 2. This is 2, right? So that is why the domain of g inverse will become x is greater than 0 but is less than or equals to 2. I hope that makes sense. Okay, so in this question we have two functions, fx and gx. So fx and gx are the same function but their domains are different, right? So I'll start with plotting fx and gx. I'll just do it in one graph because it's the same function, but the only difference is the domain. So the vertical asymptote will be, firstly I'll have to simplify this because there's plus 2, or we can transform it. Okay, so vertical asymptote will be x equals 2 because x minus 2 equals 0, right? And horizontal asymptote will be, because it's an improper rational function, so that will be y equals 0. Right now I'm only plotting this part, I'm excluding the 2 plus 2. So So x equals 2 is the vertical asymptote, right, and the x-axis is the horizontal asymptote. So how will you plot the graph? First we'll find some values. Let's take 3. If we input 3 into the function, 8 upon 3 minus 2 is 8, so that means that when x is 3, so fx is positive, that means it's in this region, right? So one part of the graph will be like this. Then automatically the second part comes in this region, but we'll confirm that. Let's find the value of fx when x is 0. So when x is 0, it's 8 upon negative 2, that is negative 4. So negative 4 is over here. So this confirms that the graph will be in this region, and it will be somewhat like this, right? So now there was one more thing given, there was a plus 2 at the end. So what the plus 2 will do is it will shift the horizontal asymptote upwards, it will shift the whole graph upwards by 2 units. What we could have done was we could have simplified this by taking the LCM and then forming a single rational function, but even this, both ways are correct. So now after the transformation of the translation, this will be the new horizontal asymptote, right? Extending the vertical asymptote. So the new graph I'll draw in red. One part will be like this. The intercept will also move upwards, so it will go to 2, minus 2. And now we can find the x-intercept, because there will be an x-intercept as the x-axis is no longer the horizontal asymptote. So for the x-intercept, y is 0, right? So for this whole thing, y is 0. So that means that 8 upon x minus 2 plus 2 should be equal to 0. So 8 upon x minus 2 equals to minus 2. So x minus 2 equals to minus 4, x equals minus 2. So the x-intercept is this. Now if I draw the other portion of the graph, it will be somewhat like this, right? So this is the graph of 8 upon x minus 2 plus 2. Now in the first part, there's, okay, so now we'll label what is f and what is g. F is x greater than 2, right? So this region is f, and gx is x greater than 2 but less than 4. So if I have 4 over here, so it's this region, right? Now they're saying first state the range of f. So for the range of f, we can see that if f is x greater than 2, that means it's this region. So over here, f is always greater than the horizontal asymptote, that is 2. So f greater than 2, right? For g is from 2 till 4. I'll find the value of y at this point. So to find the value of y, I'll input 4 into this equation, right? 8 upon x minus 2 plus 2. So 8 upon 4 minus 2 plus 2, 8 upon 4 is 8 upon 2 is 4 plus 2 is 6. So over here x is 6, right? So that means, sorry, y is 6. So it will be greater than, g will be greater than 6, because it can't come below, it's till this point and it's going till infinity over there. So g is greater than 6. In the last part, they're saying state the range of fg. Okay, so for fg, okay, so in fg, what is happening is that there's f and then gx, right? So the domain of g becomes the range of f. Sorry, the range of g becomes the domain of f, right? Range of g, we know that g is greater than 6. So in f, the domain will be x is greater than 6. So when x is 6, so what is f6? It's 8 upon 6 minus 2 plus 2, that is 4, right? So that means that basically this is 5, this is 6. So the domain that f is getting is x greater than 6, and at x equals 6, if I extend this is 4, right? This is a sketch, so it does not seem like 4, but this should be 4. So the domain of f is x greater than 6, right? So it's 4, and then there's this horizontal asymptote below it. So the range of fg will be less than 4 but greater than the horizontal asymptote, that is 2. So fg should be less than 4 but greater than 2. I hope that makes sense. So fg is greater than 2 but is less than or equal to 4. So in the next question, we are given with fx and gx, and you have to find the range of f and g. So I'll quickly plot both of them. So first, for f, the vertical asymptote will be 2x plus 1 equals 0, so x equals negative half, and the horizontal asymptote will be y equals 0, right? Sketching this graph should take just a few seconds, so this will be helpful if you do sketch it. This is negative 1, this is negative 2. This is the vertical asymptote. Okay, so if I look for the x-intercept, that means that fx is 0, so I won't get any x-intercept as the horizontal asymptote is y equals 0. But if I look for a y-intercept, so x is 0, so I'll have 3 upon 1, that is 3. So the y-intercept is 3, let's say 3 is over here, right? So I'll get a graph like this. It's passing through 3, and then 1 like this. Now they're saying that x is greater than 0 is the domain, so that means that this is 0, so x is greater than that. So find the range of f. So f is obviously less than 3 because in this region it's less than 3. It's less than or equal to 3. Oh, no, it's only less than 3 because its x is greater than 0, so we won't include the y-axis. So it's less than 3 and it's greater than 0, which is the horizontal asymptote, obviously, right? Now for the second part of for g, I'll first simplify this. I'll take LCM, and then gx will become 1 plus 2x upon x, right? So vertical asymptote will be x equals 0. Horizontal asymptote will be the ratio of the coefficients of x, that is 2 upon 1, that is 2. Right, so x equals 0, that is the y-axis is one of the asymptotes, so the vertical asymptote, and the horizontal asymptote will be at 2. Sorry, horizontal asymptote will be at 2, so over here, or let's say this is 2. So this is 2. Now I'll look for the x-intercept. So for the x-intercept, gx should be 0, so that will give me x equals to negative 1 upon 2. So negative 1 upon 2 will be over here. So this is the x-intercept, right? So I'll get a graph like this over here, and then I'll get, if I extend this, so I'll get a graph like this over here. They're saying that x is greater than 0 as the domain, so find the range of g. That means that we'll take this portion. So over here, g is greater than 2. This line is 2, so g is always greater than 2. So these are the two ranges.